So in this short lecture, I will present you the Galton-Watson process. So we are interested in studying a population. So the population will start with one individual, which will have a certain number of offsprings, let's say 3, and then each of its offsprings will also have offsprings, and so on. And you have, in this way, a random tree which you are constructing. So I will represent by x0 the number of individuals at generation 0. And x0 will always be equal to 1. So this is generation 0. Then we have generation 1, 2, 3, and so on. And we will denote by x1, x2, x3, and so on, the number of individuals at each generation. So in my example, x1 is equal to 2. At the second generation, we have 3 individuals. At the fourth generation, we have 5 individuals, and so on. So this is the main notation. And in order to build the mathematical model, which will represent the evolution of this population, let me represent by m, n, k. So that will be the number of offsprings of the kth individual of the nth generation. So n represents the generation, which is larger or equal than 0, and k will be an individual, so the kth individual of generation n. And m and k will represent the number of offsprings of this individual, which is the kth individual of the nth generation. So since we know that x0 is equal to 1, well, x1 it's exactly equal to the number of offsprings of x0, and this is with my notation, where you take generation 0, there is only one individual, and x1 will be exactly equal to the number of offsprings of the individual of generation 0. And in the same way, if I want to represent x2, well, for x2, I have to sum the number of offsprings of each individual of the first generation. So I will sum over all elements of the first generation, but this is x1. And for each element of this first generation, so I'm here interested in the first generation, well, I will just sum the total number of offsprings of this element. So I take the element j from the first generation, I compute the number of offsprings of this individual, and I sum over all individuals, and in this way I get the number of individuals of the second generation. And more generally, for any n, xn plus 1 will be equal to the sum from 1 up to xn of m, n, j. And I hope I have the right notation, and this is exactly so. To obtain the number of individuals at generation n plus 1, I count over all individuals of generation n, and for each individual, I sum the number of offsprings of this individual. So, of course, here, these random variables m, n, j will take the values 0, 1, 2, and so on. So, in my next take, I will introduce the model, and the model consists in assuming some hypotheses on these variables m and j. So I just rewrote here the definition of these variables. So remember, m and j, it's the number of offsprings of the jth element, the jth individual of generation n. We start with one individual at generation 0, and the total number of individuals at generation n plus 1 is just the sum over all individuals of generation n of the number of offsprings of each individual. And now we will state some hypotheses, some assumptions on these random variables m and j. You see that once I fix x0 to be 1, and once I fix these variables, I can define xn for all n. So what are the assumptions? Well, the easiest model would be just to assume that these random variables are IID. So I will assume that these variables, m and j, where n it's ranging from 0 on and j from 1 on, that these are IID random variables. So they are independent and identically distributed and defined in some probability space, which I do not specify. And then, well, so let's represent by pk the probability that one of these variables, so let's say m1, 1, it's equal to k. So what is the, so I'm representing by pk the probability that one individual of this population has k offsprings. So what are the assumptions on p? Well, first, I will assume that this population can decrease. So in order for the population to decrease, I will assume that the probability that one individual has no offspring, it's strictly positive. So I'll assume that P0, it's strictly positive. And also, I want to assume that this population can increase, and for that, I will assume that the probability of having no offspring plus the probability of having just one, that this is less than 1. Right? Because if P0 plus P1 it's equal to 1, what will happen is that, well, you start with an offspring, then either it has no offspring or 1. So maybe it has 1, then the second one has 1, the third has 1, and then at some point you stop. So we will get a very simple process in which the population never increases, and at some point it stops. It's very easy to compute in this case what is the probability that xn is equal to 0, and I will leave it to you as an exercise. So in order to avoid this trivial example, I will assume that the population can increase, which means that the probability of having 0 offspring plus the probability of having 1, it's less than 1. So these are the assumptions. And the problem I want to investigate, it's very simple. I want to study what is the probability that this population will extinguish. So this is what is the probability that xn is equal to 0. I would like to study well, this sequence and to prove, to examine if it converges always to 1, or if it may converge to a number which is different from 1. I want to study if this population extinguish with probability 1 or not. Note that this limit exists because if xn is equal to 0, so if there is no individual at generation n, then by this definition, you see that there will be no individual at generation n plus 1. So if xn is equal to 0, this means that xn plus 1 is equal to 0, which means that the probability that xn is equal to 0, it's less or equal than the probability that xn plus 1 is equal to 0. So this sequence, it's an increasing sequence, and it's bounded by 1, so it has a limit. And this is my question. My problem is to study the limit as n tends to infinity of this probability. I want to investigate whether this is always equal to 1 or if this limit might be less than 1. You see that in case this limit is less than 1, this means that there is a positive probability that this population will never disappear. So this is the main question which I want to address. And let me mention that this problem was proposed at the end of the 19th century by Galton and Watson. They were investigating the surnames of aristocratic families in Great Britain, and they realized that the number of surnames were decreasing in time, and so they wanted a mathematical model to explain this phenomena. And this is, so they proposed this model in order to investigate, well, whether the total number of Great Britain's aristocratic surnames will disappear at some point or not. So this is the model, and this is the question which I will address in the next takes. So I wrote here the assumptions we did on this sequence of random variables, and now let me present the how Galton and Watson solved this problem. So the idea was to introduce what's sometimes called the moment generating function. So if you have some probability space omega f, and in this probability space you have a non-negative random variable, I will define phi of x as the moment generating function of x as a function from 0, 1 to 0, 1. And phi x of theta, it's equal to the expectation of theta to the power x, which is sometimes convenient to write as the expectation of exponential x log of theta. So mind that fx at 1, if I take theta equal to 1, this is always 1, that there might be a problem defining phi at theta equal to 0, but I leave it to you to check that you can indeed define the value at theta equal to 0, and at theta equal to 0, what you get is that this is exactly the probability that the random variable x takes the value 0. So, well, these are general properties. So now let me fix random variable m. So m has the same distribution as m11. So it takes the value k with probability p of k. And let me define by phi, in order to keep notation simple, phi will be the moment generating function of phi m. So phi of theta is just the expectation of theta to the power m. And now let me justify why this is called the moment generating function. Let me take a derivative in theta of phi. So I leave it to you as an exercise to prove the following formula. What I claim is that this is equal to m to the times theta to the power m minus 1. So I leave it to you as an exercise to prove this identity. Mind that if now I take the derivative and I compute it at 1, what I get is that this is exactly the expectation of m. So the derivative of the moment generating function computed at theta equal to 1 gives me the first moment. Now if I take the second derivative of theta, then this is equal to the expectation of m times m minus 1 theta to the power m minus 2. And again, I leave it to you as an exercise to prove that this is well defined and that this identity holds. Now, if I compute that at theta equal to 1 what I get is that this is the expectation of m times m minus 1. So I can recover the second moment of m by the value of the second derivative at 1 and the value of the first derivative at 1. And you can repeat this argument to get all moments of phi, of m through the derivatives of phi. This explains why this is called the moment generating function. In our case, m takes only integer values, so you see that, well, if m is equal to 0 or 1, this is 0, so this will depend only on the values of m larger or equal and then 2. And moreover, that this is then strictly positive, which means that our moment generating function of m is strictly convex. So we have, let me draw a picture of phi. So phi is defined between 0 and 1. It takes value between 0 and 1. So so this is phi. So this is theta. At 1, it's equal to 1. At 0, so let me claim that phi m of 0 it's equal to the probability that m it's equal to 0. So let's go to the formula, and let's write phi m of 0 as this expectation, but I will divide that in two cases. The expectation when m is equal to 0, and you see that when if I write theta m as the exponential of m log of theta, let me take theta strictly positive but small, so this will be a non-negative number times 0, so that will give you 0 exponential is 1. So this is the first piece which will give me a contribution 1, and then I have chi for the points where m is larger than 1 of the exponential of m log of theta. Right, so I just decomposed phi in two cases, the case in which m is equal to 0 and m larger or equal to 1. When m is equal to 0, I argued that this exponential is equal to 1, so there is a factor 1, and then there is this factor. So now so this is phi m of theta, and I want to take theta to 0 in order to get this formula. So on the one hand, you see that I have an exponential, so this exponential, it's always positive. On the other hand, we have that m, it's larger than 1, and log of theta, it's negative, so this is bounded by exponential log of theta. Right? Here, I'm assuming that m is larger than 1, so m it's larger than 1, but log of theta, it's negative, so I reverse the inequality, and I get this, and this is exactly equal to theta. So as theta, so this expression here, it's bounded between 0 and theta. As theta tends to 0, this expression converges to 0, and therefore phi m of theta, as theta goes to 0, converges to this probability, which means that if I want to have a continuous function, I have to define phi m at 0 as the probability that m is equal to 0. So these are the properties I want to stress of the moment generating function in order to draw this graph. So let me draw here the identity. Now, I know that it's a convex function, which means that the derivative is increasing. Now, I can have two types of phenomena. Let me first draw the case in which the derivative, which I'm calling m, so m will be the expectation of m. And in the first case, let me assume that this expectation is less or equal than 1. If this expectation is less or equal than 1, remember the expectation, it's the derivative at 1. This means that the derivative at 1, it's less or equal than 1. Well, here is the identity, so derivative equal to 1. So if the derivative is smaller than 1, the function looks close to 1 as this. So its derivative is less than 1. And, well, the derivative is increasing. So what happens is that you have a function which looks like that. So it crosses the identity in the interval 0, 1 at only one point, which is at the point theta equal to 1. Well, but there is a second case in which we have a derivative which is larger than 1. So again, this is the function phi in terms of theta. There's the identity. And now let me assume that m, which is the expectation of m, it's larger than 1. So if it's larger than 1, we have seen that the expectation, it's the derivative at 1. If the derivative is larger than 1, we get a function which close to theta equal to 1 looks like that. On the other hand, I assumed that p of 0 is strictly positive, which means that phi of 0 is strictly positive. So here is the value of phi of 0. And now, well, I leave it to you to prove that the function phi will look like this. And my, well, my picture is not very good, but because remember, phi, it's an increasing function because its derivative, it's strictly positive, so it doesn't look really increasing here. But what I want you to prove using convexity is that phi cross the identity in the interval 0, 1 at 2 points. One point which is strictly larger than 0 and smaller than 1, and at point theta equal to 1. So there is a point here, theta star, a unique point theta star in the case in which m is larger than 1, such that phi of theta star it's equal to theta star. So my claim is that there exists a unique theta star, and theta star which belongs to the interval 0, 1, such that theta star it's a fixed point of phi, which means that phi of theta star it's equal to theta star. So I leave it to you to prove this claim, and you'll see that theta star will play a very important role in the solution of the Galton-Watson problem. So now, once I defined this phi, let me call phi n the moment generating function of xn. So this will be the expectation of theta to the power xn. And let me compute that. So I want relation between phi n plus 1 and phi n. So I want to compute phi n plus 1 of theta to get a recursive equation for phi n. So let me compute phi n plus 1 of theta. This is, by definition, the expectation of theta xn plus 1. But xn plus 1, I have here a definition. So this is the expectation of theta to the power, the sum from 1 up to xn of m n j. Right, so this is my definition of our model, my definition of xn plus 1. So now, let me decompose according to the possible values of xn. So this is the expectation of a sum. So xn can take values, any value p larger or equal to 0. Let's assume that xn it's equal to p. So mind that this is the indicative function of this set. So I'm computing this expression in the set in which xn is equal to p. But if xn is equal to p, what I can replace here xn by p, and what I get, that this is the sum from 1 up to p of m and j. Now, all these expressions, all these terms are positive, so I can exchange by Tonelli the expectation with the sum. So this is equal to the sum p larger than 0 of the expectation of xn, it's equal to p, and theta to the power sum from j from 1 up to p, m and j. And now what I want to claim is that xn is independent from m and j. So you see that in order to, I started from x0, which is equal to 1. Now when I define x1, to define x1 I used the variables up to x0. I used the variables m0, j. So x1, it's a function of the variables m01, m02, and so on. Now, if I want to define x2, what I want, it's a sum from 1 up to x1 of m1j. So x2, it's a function of x1 and a function of the variables m1j. But x1, it's a function of these variables. So from this, I get that x2, it's a function of the variables m01, m02, and so on, because x1, it's a function of these variables, and then also m11, m12, and so on. So if you give me the values of m01, m02, m11, m12, and so on, I can compute x2, because x2, it's a function of these variables. And generally, xn will be a function of m01, m02, and so on, and also of m n minus 1, 1, m n minus 1, 2, and so on. So if you give me the values of m01, m02, m11, m12, mn minus 1, 1, mn minus 1, 2, and so on, I can compute the value of xn. So xn, it's a function of these variables. And you see, what appear here are the variables m and j, which are not in this set. And since we assumed at the beginning that these variables are independent, this means that xn, which is a function of these variables, xn, it's independent of these variables, right? So this is an application of the results we've seen in the lectures, which tells you that, well, if you have a function of a family of independent variables, then this new function, it's independent from these independent family. So it follows from this argument that xn is independent from m and j, and therefore that this expectation, it's equal to the product of the expectations. So I can rewrite this sum as a sum of, well, the expectation of this characteristic function, which is the probability that xn is equal to p, and then the expectation of this expression. But now I can use the fact that these variables are IID to rewrite this expectation. So I have here actually a product of functions. Since they are independent, this is equal so to the product from 1 up to p of the expectation of theta, m, and j. But since these variables are all identically distributed, and I represent by phi the characteristic function, the moment generating function of m, this is all these variables are equal to phi of theta, and since I have m of them, this is phi theta to the power p. And well, so what appeared here is the sum over p, that the probability of that xn is equal to p, times phi theta of p, and this is equal to the expectation of phi of theta xn. And well, now if you observe this equation for the moment generating function, what you see here is that this is the moment generating function of xn applied to phi of theta. So this is phi n of phi of theta. So we obtained the recursive relation that phi n plus 1 of theta is equal to phi n of phi of theta. So let me erase this expression and rewrite what we just proved. We proved that phi n plus 1 of theta is equal to phi n of phi of theta. And now I can iterate this relation and apply this relation to n minus 1. So I will get that this is phi n minus 1 of phi applied to phi of theta. And phi applied to phi of theta, so let me represent by phi 1 the function phi, and by phi k plus 1 the composition of phi k composed with phi. So with this notation, this is exactly phi second, so the composition of phi with phi. So if you want phi of k, in this notation will be phi composed with phi k times. And what we get, so that this is equal to phi n minus 1 of phi of 2 of theta. And if you iterate this relation up to the end, what you get is that phi n plus 1 of theta, that this is equal to the n plus 1 iterate, the n plus 1 composition of phi with itself computed at theta. So let's go back to the original problem. We want to investigate the limit of the probability that xn is equal to 0. But we have seen that this probability, it's actually the moment generating function of xn computed at 0. And now we just proved, and this is what we called phi n of 0, and we just proved that phi n of theta is actually the composition of phi with itself n times, which has been represented by phi n this way, and this is computed at 0. So actually, if you want to study the probability that xn is equal to 0, what we need is to consider the moment generating function phi of m, compose it with itself n times, and compute the value of this iterate at 0.0. So now we can complete our argument. So we proved that the probability that xn is equal to 0, it's the, you take the moment generating function of m, you call that phi, you compose phi with itself n times, you compute that at 0, and you get this probability. So here we have seen that there are essentially two typical behavior. One, if m is less or equal than 1. So remind yourself that m, it's the expectation of m, which is the mean number of offsprings in this population. So if this mean number of offsprings is less or equal than 1, this is the behavior of the moment generating function, while if m is strictly larger than 1, this is the behavior. And this depends because we have seen that the derivative at 1 is exactly equal to m. So if m is less or equal than 1, we have this type of behavior, while if it's strictly larger than 1, we have this type of behavior. Now, we can compute phi n of 0. So let's start with phi of 0. So here's 0, so phi of 0 is this value. And now I want to compute phi of 0. So I want to compute phi 2 of 0. So how do I do that? Well, this is phi 0. I want to find phi of 0 in the x-axis. So in order to do that, I have to go to the identity. Once I reach the identity, I have exactly what is phi of 0. So this is phi of 0. And in order to compute phi 2 of 0, I just have to compute phi at this point, which I get is this point. So this is phi 2 of 0. And so you see that the way in which you do that, you start with phi 0, you go to the identity, to the diagonal, and then you go to the function. And this is phi 2 of 0. So now if I want to compute phi 3 of 0, I repeat exactly the same procedure with phi 2. So I'm at phi 2, I want to find phi 2 here, so I go to the identity. Here is phi 2 of 0, and now I want to compute phi 3, so phi 3 is this point. And so on. So if I continue, I'll go to the diagonal, I go to the function, to the diagonal by an horizontal line, and to the function by a vertical line. And in this way, you see in the picture that it's clear that phi of n at 0 will converge to 1. So this is the claim, and how you prove that? Well, what you prove is that phi of n of 0, it's an increasing sequence. It's an increasing sequence, and it's a sequence which is bounded by 1. So it has a limit. Call this limit alpha. Now apply phi to both sides. You see that phi is a continuous function, and by applying, since phi is a continuous function, what you get by applying phi on both sides, you get that phi n plus 1 at 0, it's converging to phi of alpha. But you know that phi n plus 1 is converging to alpha, which means so that this implies that phi of alpha is equal to alpha. And the unique point, the unique phi in the interval 0, 1 has a unique point which satisfies this identity, which is alpha equal to 1. So this implies that alpha equal to 1. So this is the unique, this is what's called the fixed point of phi. So the unique fixed point of phi in interval 0, 1, it's 1, which means that alpha is equal to 1. So we just proved that if m is less or equal than 1, then the probability that xn is equal to 0, so that the probability that this population, this family will disappear, converge to 1. So eventually, this family will disappear. So now let's see what happens in the case in which m is strictly larger than 1. Well, when m is strictly larger than 1, we have seen that the derivative at 1, which is m, is strictly larger than 1. So we have a function which is convex, whose value at 0, it's phi of 0. So it's the probability p of 0, it's strictly positive. And it has a unique fixed point, which we called theta star. So theta star is the unique fixed point of phi, and this is the this is what we call. So now let's repeat the same argument. We want to compute the iterates of phi of 0. So we start with phi at 0, which is p of 0. So this is phi of 0. Now we want to compute the second iterate. So we have seen that we have to go to the diagonal. So this is phi of 0 and compute. So here is phi 2 of 0. And you iterate that procedure, and you see that you are converging to theta star. And the same argument I presented before tells you that indeed phi n of 0 converges to theta star. So we know that phi n of 0, it's increasing. It's also smaller than, so phi of 0, it's smaller than theta star. Why is that so? Because, well, you know that 0, it's smaller than theta star. Phi, it's increasing. Apply both phi on both equations. Since theta star, it's a fixed point, I get that phi of theta star is theta star, while for 0, I get phi of 0. If I iterate that n times, what I get is that this sequence, it's always bounded by theta star. It's increasing, it's bounded by theta star, it has a limit, call that alpha. Conclude that alpha, it's a fixed point, and therefore that the unique fixed point alpha has to be less or equal than theta star, because each point, it's bounded by theta star, and the unique fixed point in 0 theta star, it's theta star. So this argument tells you that in the case in which m, it's strictly larger than 1, then the probability that xn, it's equal to 0, converge to theta star, but theta star is strictly smaller than 1. And this there is a fixed point theta star which is strictly less than 1. And this shows that the probability that xn larger than 1 for all n, that this probability is equal to 1 minus theta star, which is strictly positive. So what we proved in the Galton-Watson model is that there are two behaviors, two phases, say. One in the case in which the average number of offsprings is less or equal than 1. In this case, the family disappears with probability 1. And one in the case in which the average number of offspring is strictly positive. So there is, in this case, a positive probability that this family survive. Of course, there is a probability, theta star, that the family will disappear. It can disappear at the first generation, right? With probability p of 0, xn is equal to 1, and this is strictly positive. So there is a strictly positive that this family will disappear at the first generation. What we are proving is that, well, there is a probability theta star that it will disappear, but this theta star is strictly less than 1. And therefore, that this family may survive with a positive probability. And this concludes the investigation of the Galton-Watson model, because well, this answers if indeed the mean offspring is less or equal than 1, then the family disappears, and this explains why the aristocratic surnames in British families were disappearing in the 19th century, just because the number of offsprings was not strictly larger than 1. Let me just conclude with a remark. So let me call theta star. So remember, is the fixed point in the supercritical case. So let me call m larger than 1 the supercritical case, m equal to 1 the critical one, and then m less than 1 the subcritical case. So let's assume that we are at the supercritical case. And let's call theta star the fixed point of phi. So phi of theta star equal to theta star, and theta star belongs to 0, 1. And I don't want to write it theta star, so let me call it alpha. Now what I claim is that the expectation of alpha xn, that this is a constant. So actually, this computation would show that alpha to the power x theta n, it's a martingale. But since I did not introduce what martingales are in these lectures, let me just prove that this expectation is constant in time. So let's compute the expectation of alpha to the power xn plus 1. So this is equal to the expectation of alpha to the sum from 1 up to xn m and j. And again, I will place here the indicator function that xn is equal to p, and I will sum. So since I did this computation already, so let me just put here the sum of p equal to 0, the probability that xn is equal to p. And what we have here is that the expectation of alpha, I'm also using the fact that xn is independent from this variable, which I already proved. And here we have a sum from 1 up to p of m and j. Right, but this is equal to the expectation of alpha m to the power p. Right, but what appeared here, it's exactly, this is the expectation of alpha to the power m, but this is phi of alpha. Right? Expectation, by our definition of alpha, the expectation of alpha to the power m, it's phi of alpha. And since alpha, it's theta star, it's the fixed point, so this is equal to alpha. So what appeared here, it's this expectation alpha n, which is phi alpha to the power p, but phi alpha is equal to the p, so this is alpha to the power p. So I can erase this expression and replace that by alpha to the p. So I'm erasing this expectation, I'm placing that alpha to the power p, and what you see now is that this is exactly equal to the expectation of alpha to the power xn, and this is what I claimed, that this expectation of alpha to the power xn, it's constant in time. So this is a first observation, and as I said, actually what can prove that alpha to the power xn, it's a martingale. The same computation tells you that this is a martingale. Well, this is one point. The second point I want now to say is that in the critical case, so now let's take the critical case. So that is m equal to 1. What I'm claiming is that the expectation of xn, it's constant. Well, and why is that so? Because the expectation of xn plus 1, it's equal to the sum from 1 up to xn of m and j. So let's again decompose that according to the value of xn, and then use the independence. So this is a sum for p larger or equal to 0, then the probability that xn it's equal to p. And here I have the expectation from 1 to p of m and j, but this is, well, they are, okay, so let me write. So here I have a sum from 1 to p of the expectation of m and j. But now all these expectations are equal because these variables are identically distributed, and the expectation is m, which is 1 because we are in the critical case. So this is 1, and here I have a sum from 1 to p. So these sums gives me 1 m times p, which is p. Right? M is 1, m times p is p. And what appeared here is that I have the probability that xn is equal to p times p, and this is the expectation of xn. So we see that in the critical case, the expectation is constant, while in the supercritical case, the expectation of alpha to the power xn, that this is constant. This does not change in time. Well, and so you see here, this might look puzzling, because on the one hand, we know that xn is disappearing with probability 1. So xn is converging to 0 with probability 1. On the other hand, its expectation, it's constant in time. While if you take the subcritical case, you can prove that the expectation is decreasing exponentially. In the supercritical case, the expectation will increase exponentially, but in the critical case, it's constant. And, well, it might be puzzling if you think a bit that on the one hand, xn is converging to 0, so xn is disappearing. On the other hand, the expectation is constant. This means that if you repeat this experiment many, many times, well, you have some families which will disappear, but the other ones will grow, and will grow in such a way that the expectation will, if you do the expectation among the size of all these populations at time n, you get something which is constant. So many of them disappeared, so many of them have no offsprings at generation n, but the ones who have offsprings at generation n are very large to compensate the fact that the other ones are disappeared. So the typical, so there is a typical behavior. Either you disappear or your family is very large in order to keep the expectation constant. And with this observation, I conclude this lecture.